So we'll start with Chunyi Gai at Dalhousie University, who will tell us something about spike dynamics in the presence of noise. Thank you. Go ahead.
Okay, thank you very much. So today my topic is the effect of noise on spike dynamics. And this is joint work with my supervisor, Theodore Kolokonnikov, David Aaron, and his PhD student, John Ramsey. So at first, I'd like to give this list of what I'm going to talk about today. So at the beginning, I'd like to introduce the model we use and also some background information. And then we add the white noise in the system, and we then studied the motion of a single spike equilibrium. Then this yields the next two topics. When noise is small, then the spike is moving around the center of the domain within a subinterval. So we then studied the distribution of spike positions. And on the other hand, when the noise is getting larger, the spike will eventually hit the boundary. And in that case, we can compute the expected time for a spike to hit the boundary. And in the end, we considered another type of noise, which is called additive noise. And in this case, we found some new problems that we'd like to study in the future. Okay, so let's look at the model. So here we concentrate on the classical Giro-Menhardt model, which contains these two equations. So here, U and V, they are concentration of activator and inhibitor. And the key assumption we made here is the activator diffuses much more slowly than the inhibitor. So here we take this epsilon to be much smaller than 1. And with this assumption, we can, a key feature for this system is that it can produce localized spike patterns. So here is an example of single spike patterns. And here we can see this blue curve is a solution for U, and this yellow curve is for V. So so here is how we construct these spike patterns. So basically, we consider the whole domain in two types. One is called inner region, and that's the region that contains the spike. And the other part is called outer region. So in inner region, since the extent of the spike is order epsilon, so here we introduce an inner variable, which is y equals to x minus x0 divided by epsilon. And this x0 is the location of the spike. Then by expanding U and V and collecting the leading order terms, we then get this system. And with normal boundary conditions, we get V0 is a constant that is to be determined, and U0 is solved as V0 times this such square function. So then to determine the value of V0, we then match the inner with outer region. So that then we solve the V equation in the outer region where we can approximate the term that contains U as a multiple of delta functions. So this means if we go back to this system, for this equation, we can approximate U squared over epsilon as a delta function. So solving this equation, we finally get V0 is, this number is 1 over 6 times G0. So G here is a Green's function that satisfies this equation. And finally, solving that equation, we have G0 is given here. So after we get the spike patterns, we then can study the motion of the single spike pattern with and without noise. And let's first consider the case when there is no noise. So to analyze this problem, we first expand X around the location of the spike x0, and we let x0 be the function of a slow time. And then by plugging it into the system and collecting epsilon order terms, we then get these two equations. And from here, we then can derive this ODE, which describes the motion of the spike. So from this equation, it's easy to see that x0 equals to 0 is the steady state, and the corresponding eigenvalue is negative. So the equilibrium is always stable. So this is a simulation of this spike motion problem. So initially, we have this spike located at 0.5. And as time goes, we see that it moves to the center and stays there. So this shows the spike is, the equilibrium is stable. Okay, now we consider the noise term. So here to understand what white noise is, we consider how to add it in the numerical simulations. So here what we do is we add a normally distributed random number at each match point and each time step. And the drawback for this is that the noise magnitude is related to the total number of match points, which is capital N. So we must be careful when choosing this N. Basically, it cannot be too large. And also, since it's hard to analyze it in the analysis using this definition, so here we use an equivalent formulation, which is shown here. So that is, we define the Gaussian white noise in this form, where phi m and this psi m, they are independent standard normal distributions. And also, if you compute the variance of this W, the variance will be will be capital N. So this picture is to check this Gaussian white noise, and it's generated by the code shown on the left-hand side. So here we generate the Gaussian white noise using this formula, and then we plot the histogram of this white noise divided by root of N, and then it gives this Gaussian distribution with mean 0 and standard deviation is almost 1. So then we add this noise term into this model. And here we have two choices. One is we put the noise term into the equation for inhibitor, which is this term. And note that here we multiply this noise by this term U, so that it has no effect outside the spec, since U is 0 in the outer region. Okay, so now let's see what happens if I add this term in this equation. So here I have a simulation for this case. So as you can see, the height of the spec is oscillating because of this noise term. But other than that, the noise has almost no effect to the spec dynamics. Okay, so we then consider the other case where we put the noise term in the other equation, the equation for activator. So here is the simulation for this case. And in this picture, we record the location of the spec. So in this case, as we can see, not only the height is oscillating, but also the motion of the spec is affected by the noise term, which is a more interesting problem to study. Okay, so we then study this problem where we put this multiplicative noise in the equation for activator, and here we apply the normal boundary conditions. Since the motion of the spec is affected by the noise term, so here we'll construct the spec motion equation just as we did when there is no noise. And in this case, it turns out a stochastic term comes into this ODE. So now in the right-hand side, we have two terms. One is the deterministic part that pushes the spec towards its equilibrium, which is in the center. But the other term, this stochastic term, can push it away from the center. So now the question is how to evaluate this stochastic term. So what we do is, since in this integral it contains this W, which is defined as the sum of normally distributed random variables. So here what we do is we combine all these variables into a single normally distributed term. And we want to compute the variance of this term. So here we compute, this is a standard derivation of this single random variable, which is given by this expression. And by plugging this W, and after some calculations, we finally get this sigma star is this number. And the key point here is this is a constant that's independent of the total number of the grid point n. So we then obtained this stochastic ODE where we replace the integral by this single random variable. So here psi is normally distributed and the sigma star is given here. So after we get the stochastic ODE of the spec motion, we can look for the distribution of spec positions. And this can be obtained by solving the corresponding Fokker-Planck equation. So for this problem, we start by considering the general case, and we denote this rho xt be the probability the spec is at position x and time t. Then the probability density satisfies this Fokker-Planck equation with the initial condition rho at x0 is a delta function. So here we're looking for the long-term equilibrium density distribution, which is the steady state of this equation. So by setting rho t equals to 0 and integrate, we then get this equation where this k is the constant. And since here we assume the noise is small enough, so the spec has almost zero chance to hit the boundary. Therefore, we must have the boundary conditions are rho at plus minus L, and the derivative rho x at plus minus L is 0. And that gives this k must be 0. So solving this equation, we finally get the density distribution is given by this function, where this capital C is such that integral of rho equals to 1. So that's the general case. And for our problem, we just need to replace F and sigma by the terms in this equation. So basically, F is this deterministic part, and sigma is sigma star. Then we can get the corresponding stationary distribution, which is shown here. And in this figure, we compared our results with the fall simulations. So here, this red curve is plotted using this formula, and this distribution is obtained by fall simulations of GM model. And we can see they matched really well. So we then did further analysis by considering the limit case of small sigma star. So in this case, we can approximate our result by Gaussian distribution, which is given here. And actually, this approximation works very well. In these two pictures, we compared our results for different parameters. So on the left-hand side, we choose the domain size L to be 1, and on the right-hand side, we choose L to be 5. And for these different curves, we choose different sigma star. So from top to bottom, we choose it from 0.1, 0.2 until 0.5. So we can see, and also we compare the exact result and this Gaussian approximation, and we can see they all have a really good agreement. So for this result, we have assumed the noise is small. So we can see the probability for the spec to reach the boundary is almost 0. However, as you can see, so as we increase the noise, from the top to bottom, we choose sigma star from 0.1 to 0.5, the distribution is getting fatter. And for even larger noise, there will be non-vanishing chance for the spec to reach the boundary. So in that case, this distribution result actually doesn't really work. But in that case, we can actually predict how long it takes for the spec to hit the boundary. So here we consider it as a mean first passage time problem. And still, to solve this problem, we start by considering the general case. And here we denote this m of x is the average time it takes for a particle to hit the boundary. Then this m of x satisfies this equation with the boundary conditions. They are m at plus minus L equals to 0. Since if you have a spec located, if initially you have spec at the boundary, it hits the boundary immediately. So then solving that equation, we finally get the solution is given by this equation where VH is this exponential function. So for our problem, we can replace f of x by this term, and then we can plot the mean first passage time explicitly by the computers. But to do further analysis, we consider two limit cases. So one is sigma star is small, and the other one is L is large. So for one case where sigma star is small and we take L is order 1, in this case, we can apply the Laplace method to approximate our result. And after some algebra, we get the mean first passage time can be approximated by this formula, where the maximum of this function, that is by setting x equal to 0, is given here. And for the other case where we assume L is large, and in that case, we can approximate f of x by almost 0 when x is much less than L. And in that case, we can approximate our result as this function. And still we can get the maximum of this function, which is by setting x equals to 0, and the result is shown here. So in this picture, we compared our results and we did some simulations. For the top row, we plot the mean first passage time for different parameters. And also we compared the exact and asymptotic results. And in the middle row, we compute the maximum of mean first passage time, that is m at 0, and still we compare this value between the exact and asymptotic results. And for the last row, we did Monte Carlo simulation of the GM model. So basically, we start the spec so we have a spec started at the middle, and we run the simulations until the spec hits the boundary. Then we record the hitting time and repeat this process for like 10,000 times to generate this distribution. And for these black lines, they are the mean value of the distribution. So this solid line is the true mean value, which is obtained by the numerics. And these two dashed lines, they are obtained by our analysis result. So finally, we considered another type of noise, that is the additive noise. So recall that the noise we have discussed, it contains the term U, so that it has no effect outside the spec. And now we'd like to get rid of this U, and we consider this noise and see what happens in this case. So here is a simulation with the additive noise. So let's have a look. So still here, I have in the lower picture, I record the location of the spec. And as we can see, now in this case, we have some background noise in this system. And if you choose the additive noise properly, the behavior of the spec is kind of similar to the multiplicative case. So basically, we can study the same questions we just did for the additive noise case. And here we computed the stationary distribution of the spec positions, and the result is shown here. The calculations is kind of similar to the multiplicative case. Basically, a big difference is that this sigma star have to be recomputed. However, for the additive noise case, we also found some new phenomena. So that is, this noise, it affects not only the spec motion, but also the stability as well. So finally, I have this simulation where we have the additive noise, and we can see some new problem. So initially, we have a boundary spec located on the right side, so that we don't have to worry about the spec motion. And after a while, you will see like somehow this spec, one more spec comes out, and this spec gets killed, and it comes out again. So for this spec stability problem, apparently it cannot be captured by the spec motion equation. So we'll consider this problem in the future. So that's all for my presentation. Thank you very much.
Thank you very much for a nice talk. Do we have any questions? You're welcome to raise your hand or type them into the Q&A. If not, while we wait, one question I had for this additive noise case, which is kind of interesting, is U also takes negative values, right? So in physical, yeah, go ahead. Well,
yeah, I mean, yes, so it can have negative value because of noise term, right?
So do you know of ways to kind of either interpret that, right, in terms of whatever the reaction diffusion process is modeling, or alternatively use additive noise which preserves positivity of the solution? Is this something you guys have thought about?
Actually, no, since if you don't have noise term, the U term actually it's a spike and it's 0 in the out region. So when you have noise, you'll get some this oscillation around 0 there. Right. We didn't really consider like how to, since I know what you mean, since it's actually it has some realistic meaning in life. So we really don't want the negative of the solution. But right, so here we haven't considered that part, right?
Yeah, and then Christian asks, how do you define the location of the stochastic spike?
So in the simulation, we just record find the maximum of this spike. So it may not be the locate yeah. So that's approximate. That's yeah. That's how we find the location of the spike. We just record the maximum of the spike, right?
Okay.
Yeah.
And then and then Daniel asked, were there differences between additive noise in activator and inhibitor? Did you look at additive noise in the inhibitor, or?
Yes, but I think in that case, still you have some background noise, and still you don't have really say much difference for the spec motion. It's still just the height. So the height is oscillating for that. Still, when you have no additive noise, so the height is oscillating, right? But
and did you include the additive noise on the inhibitor equation, or did you only look at additive noise? Okay.
Yeah, we looked at that. We did that simulation, but still, we don't see much difference for the motion.
I see.
Yeah.
Okay. And then finally, Vaslav was asking if you could talk about the assumptions of the boundary conditions on the distribution function f. So I think this is when you were talking about the Kolmogorov equation. What are sort of the boundary conditions?
Yes, exactly. The slide we just saw.
Sorry, this one?
Yes. Oh, so it's not f. It's yeah. So I was a bit puzzled that you have this assumption for distribution function and its derivative at the endpoints to be 0, but I couldn't see then how the spike could travel all the way to the boundary then if you prescribe the boundary condition to be such.
You mean for this boundary condition, like rho and plus minus? Yeah. So since in this case we assume the noise is small, so the spike cannot reach. Not cannot. It's like you can if you want to wait, maybe we need to wait like forever for the spike to reach boundary. There is like a really small chance for the spike to reach the boundary, right? So in that case, we have this boundary condition like rho. The probability for the spike to reach plus or minus L is 0. Yeah, and similarly, you can see that the boundary the derivative at plus minus L is also 0. And if you have these two boundary conditions and plug it into the equation, that gives this k has to be 0.
Okay.
Does that make sense?
Thank you.
Yeah.
Okay. Well, is there anything else? If not, we can move to the next speaker.
Thank you very much.
Okay. Well, thank you very much for a nice talk.